All right, everybody, welcome. Thank you for joining us for another virtual stargazing program. For those of you who don't know me, I'm Samuel Singer, the founder and executive director of Wyoming Stargazing. And with me tonight is our vice president of the board of directors, Mike Adler. Mike's at his house just outside of Jackson, and he's got a pretty fantastic telescope that we've got some cameras hooked up to, and we're going to show you some cool stuff tonight. So Mike, thanks so much for being here with us.
Oh, thank you so much, Samuel.
All right, Mike, whenever you're ready, I'm going to stop sharing my screen and you can share yours.
Okay.
And then we can get going.
Okay. All right. So I will share my screen. I have to find the application first. See, you are screen sharing. Stop share. All right. Okay, there you are. Okay, now I'm going to share screen. Okay, so let me talk to you a little bit about what this is all about. There's a couple of screens here. This one is, let's see, no, people aren't seeing this, are they?
They are, yep, they're seeing all that.
They are, okay, okay. I am sharing my desktop. This application is called SkyX, and it actually controls what the telescope does. There's another application right here, and this application it takes cameras. So what we're looking at is not actually, obviously you're not sitting here by my telescope looking through an eyepiece. What you're going to be seeing are images that I'm taking, short images that I'm taking with the camera that's attached to the telescope. Now the telescope happens to be a 20-inch reflecting type of telescope. It's cardiotropic is the technical term. Corrected Dahl-Kirkham is the actual what it is, and it's a plane wave telescope. So we're going to be using its 20-inch telescope and looking at a bunch of objects. Now, it just so happens Samuel and I were looking at some things before you joined us, and we just happened to be pointing at something. So we may as well look at that object first, since it's right here.
Sounds great.
It's called and here it is. And it's a picture I've already taken, and I won't push my luck. No, we could retake it, but let's look at it first, and then I'll take it again. But if for somehow a cloud has gone by or something, this way we at least have we've seen it. So I just changed the. So this is called the Bubble Nebula, and it's what's called an emission nebula. Actually, like a lot of them that we're going to see tonight. And what that means is this bright star that's right here is exciting the gas in this nebula. Nebula is made up of dust and gas. And in an emission nebula, there's gas in it that's hydrogen. In this case, I know there's hydrogen gas, oxygen gas, and sulfur gas. And so this bright star is exciting the gas, and then the gas gets excited to a higher energy state, like hydrogen is lifted up into one of its elements, and then it decays and re-emits the light, and so that's why it's called emission. And so what we're looking at actually is the light that's emitted by in this case, most of it's hydrogen gas. And this is called the bubble because if you look really closely right here, you can see almost what looks like a person's head, and that's the bubble. And it's this bright star right here. The solar wind from that bright star is actually inflating this bubble of hydrogen gas and creating this bubble shape. And so that's called the Bubble Nebula. And if I zoom in a little bit more, I'm not sure it looks any better, but you can see it. And yeah, these vertical lines, by the way, are an artifact of the chip. When you really have very high exposures, it turns out the charge overflows the pixels where the star is and flows into the adjacent pixels, and so these lines are not real. But anyway,
And you're talking about the chip on the camera, right, Mike?
the chip on the camera, right? The chip on this camera. It's this camera is about a 4,000 pixel by 4,000 pixel camera. So it's a fairly high resolution. It's about 39 millimeters square. It's not a 35 millimeter camera. But it's about the same size as a full frame 35 millimeter chip, but it's square and it's not rectangular. Anyway, so this is the Bubble Nebula, and you can see some of the gas around it too. So this is so this is pretty nice. We don't often in these short exposures, we don't often see this, and it's nice that we're getting a fairly good night here, I think, for viewing.
The Bubble Galaxy. Oh, go ahead, Joanne. Oh.
No, don't worry. I'm just commenting to myself.
Oh, okay.
Anyone has any questions, just speak up.
Yeah,
it's a fairly informal process here.
And I was just going to mention a couple things about this object. So this object is pretty far away. It's 7,000 light years away. To put that into a distance we're probably more familiar with, each light year is 6 trillion miles. So 6 trillion times 7,000, that's 42 quadrillion miles away. So that's what we're looking at here. A star that's puffed out some of its gas 42 quadrillion miles away from us. And Mike, do you recall the size of the Bubble Nebula?
Off the top of my head, I don't, but most of I can wing it, and I won't be too far off.
I just looked it up.
I'm guessing it's on the order of several hundred light years.
It's actually a little bit smaller. So just the bubble itself is actually only 3.5 light years.
Oh, okay.
But if you take the entire nebulosity, it's probably a lot more than that.
Yeah, well, I was thinking of the bigger picture, but yeah.
Yeah, that's probably closer to 50 or 60 light years.
Yeah, right.
Yeah, so that little bubble right there is about 25, let's see, we said 3 light years. Yeah, so 25 trillion miles across.
Yeah, just as a way of also calibrating that, our nearest star, other than the sun, is about that distance away. It's about 4 light years away. And
Right.
just to give you a feeling for how small, Pluto, which the New Horizons satellite went by several years ago, is something on the order of several billion miles away. Billion, not trillion, not hundreds of trillions. And so you could and it's on the order, like Mars, I know, is like 15 light minutes away. The sun is 8 light seconds, 8 light minutes away. Mars is 15 light minutes away. Minutes, not years. And I think Pluto is maybe an hour, light hour away, or several light hours.
Just over 10.
10 light hours. Yeah. So, but you think about our nearest star is it is 4 light years. Think how many hours there are in a year. I mean, it's just way further away. So, our solar system, and it took the New Horizons satellite 10 years to get there, and so it just puts everything a little more in perspective when you think about the size. As far away as that is, which is impressive, it's still very close to us compared to this object, which Samuel said was 7,000 light years away, and its size being 30 light years across for this bubble.
3.5, yeah.
Yeah, amazing.
Okay.
Can you explain the white lines a little more?
Yeah.
If it's spillover,
yeah,
from one pixel bucket to the next,
yeah.
Why are all the stars around the lines there as dots?
Well, they aren't. If you look, I mean, the line is fairly narrow. I mean, uh, well, here's one that went right through it too. So it doesn't totally saturate the pixel, is what I guess is going on. It lightens it up, brightens it up, but it doesn't, because this one I can see a star right through it.
Hmm.
Yeah, you're right. So yeah, this one doesn't quite hit it. And also the other feature, the other thing that we're doing to make these images bright like this is that I'm doing what's called a super pixel. This to make this bright enough so that we can see it in a short exposure. Uh, I'm binning 6 pixels together on a side so that this is a super pixel. So it's normally when I take pictures, I'm doing it with pixel by pixel to get the full resolution of the camera. But here, so everything is being broadened and blurred a bit and for our purposes here, it works just fine. But you have to ignore these bright lines.
Mike, why don't
Okay,
I pull up an image that you processed
of this image, yeah.
So folks can see what it looks like when you have a long time exposure and do all the different filters and combine them together.
Okay, shall I stop sharing here and I'll
No,
let
you're
you?
good. I think I was able to just take over. Somebody give me a thumbs up if you can see this picture of the bubble nebula. Can you guys see that now? All right. Thanks, Scott. Appreciate it. So yeah, so here's a really lovely image that Mike took in true color. So I believe all the red here is hydrogen gas. And just to remind everybody the size of just this bubble portion, if you put the sun on one side of this bubble, the closest star to our sun, Proxima Centauri, would be on the other side of the bubble, just about, more or less, about 4 light years away. This bubble is just 3.5 light years. So Proxima Centauri would be just beyond that bubble. So this is enormous, 25 trillion miles across.
Okay.
Mike, what do you want to go to next?
Okay, well, you and I were looking at a couple of things. So should we try well, we could do the Veil Nebula or
Yeah, let's do that.
okay, let's try that. And okay, so what I'm going to do is just manipulate, change the screens a little bit, go back to the screen that controls the telescope, and I'm going to look at an object which has this a beautiful name that rolls right off your tongue. It's called NGC 6962.
92.
92. Okay, 6992. There you go. 6992. Okay. Then I'm going to hit find, and it's right. So that object is right over here. The telescope is pointing here. So I will now tell the telescope to go there, and it's going to do what's called a flop for an equatorial telescope, but I won't bore you with what actually that means, but it's flipping itself around so it can look at this object. But you can see it moving. The yellow dot is the actual where the telescope is pointing at all times. And it's just about there. Okay, and now the computer or the program is telling me it's now tracking, so it's now pointing at that object. Just as a note, it's these two colors here, the blue and the reddish maroon color. Right in between it is the meridian. So this is pointing right over our heads right now, almost, this object. Okay, so we're going to move that out of the way, go back to the, this program is what controls the camera on the telescope. And so now I'm going to take a picture of this object, and I'm going to, so I'm going to take a 20-second picture of this object.
This object's going to look a little bit different than the last one. It's not an emission nebula of a single star illuminating gas around it. What we're going to look at now is a supernova remnant. So this is the leftover remains of a really massive star, about 20 times the size of the sun, that exploded somewhere between 10 and 20,000 years ago. And we're just going to be looking at the debris field, what's left over of this star.
Oh, there it is. Unfortunately, it's not quite as good as there may be a cloud in the way here, but it's, oh, there it is. You can see it. Yeah, there's a certain amount of haze here. The veil, as Samuel was saying, is a supernova remnant. Now, it is emission in the sense that the stars in the area are causing what the leftover gas. In this case, it's most of the gas is oxygen and some hydrogen. So I don't, in this case, if we look at a picture of the Veil Nebula, maybe after we finish with this, you can see the colors where the red is hydrogen and the blue is oxygen. But that's what we're looking at. And unfortunately, there's also there's a cloud in the way, so that's what this haze is. You'll notice that these stars in this case are not producing these vertical lines because none of these stars are as bright as that star was in the previous picture.
Maybe let's try snapping one more picture, Mike, and see if it was.
Yeah, maybe it'll be a little better. I'm gonna go to let me try the 4-binning and let's see what 30 seconds looks like on this one.
All right. Well, while we're letting that expose, I'll bring up a picture of what this looks like. That's been processed. Another one of your pictures.
Yeah.
So this is what we could see if we spent, what, maybe 10 or 20 hours of exposure time, Mike?
Right.
And is red hydrogen here and blue oxygen?
That's correct. Yes. Yeah. This is not what there's a couple of color schemes that people use when they're doing these narrow band. This is what when you're taking pictures with narrow band filters, that is filters that only look at the hydrogen at the emission from these various gases like hydrogen or oxygen. Those are called narrow band filters, and they're known as false color because you assign a color. But in that image, the colors are fairly close to the true colors because hydrogen does emit in the red and oxygen does emit in the blue, green blue. And so that's fairly close to what it actually is. But Hubble has popularized a different color scheme. So many of the pictures you see from Hubble, and frankly my own pictures, are done in what's called the Hubble palette, where hydrogen is green and oxygen still is blue. But anyway, it makes the pictures look quite different. Unfortunately, this picture still looks about the same. We could maybe come back to it a little later and see if it clears up. But
you want to try playing with the histogram a little bit, see if we can bring it
yeah, well, we can, let's see. That's a point. Maybe I shouldn't be on the high setting. Let's try the medium setting. Well, that doesn't help much. Yeah.
Yeah, we can come back to it. That's a little better.
Yeah. Okay.
Yeah, we'll come back to it later this evening.
Yeah, unfortunately, we saw it a little nicer earlier, but there are some clouds moving in and out this evening. So. Okay, shall we move on to something that's fairly close to this one? We'll try M27.
Yeah, sounds good.
Okay. So M in this case stands for Messier and is out of his 110 objects that he found. He was actually looking for comets, and he happened to see all of these other things. So even though he found a lot of comets, these were things that he saw in addition to the comets. And that's frankly what he's most famous for now, is not the comets he found, but for this catalog of 110 objects. Well, this is the Messier 27. Now, that other object, which we call NGC, something stands for New General Catalog. Anyway, these are just various catalogs of astronomical objects. Okay, so we're now pointing at, I found, let's see, I have to say find it. It's not very far away, as you can see on my screen. And now I'll tell the telescope to go there, and didn't have to go very far, so it's there now, and we'll go back up to the picture program, camera program, and take a picture of it.
So Charles Messier, he was alive in the late 1700s, early 1800s, I believe.
That's correct, yes.
And I think he is credited with discovering something like 7 or 8 comets over the course of his life.
Okay. All right, well, there it is. So this one is medium.
That looks nice.
Okay.
Yeah,
that's so this is what's called a planetary nebula, and it has nothing to do with a planet, however. It's just round, so they call it a planetary nebula. This is also just like the object we were just looking at, the Veil Nebula, which is a stellar remnant, a remnant of a star that is no longer with us. In that case, it was a supernova. Big stars blow up and create supernovas. Smaller stars, like our sun, for example, when they wink out, they don't explode. They just simply burn through all of their gas, burn through all the hydrogen. Our star is still burning hydrogen. Once all the hydrogen is gone, it will burn. What it's doing in the process of burning the hydrogen is converting the hydrogen into helium, and with the leftover energy, there's less mass in the helium than there was in the hydrogen, and there's the leftover energy is the light and the heat that the sun produces. Well, once the hydrogen is gone, the heat disappears, the gravity takes over, squeezes the helium, and lo and behold, the helium actually starts another nuclear reaction, converting helium into carbon. Well, when the helium is all gone, it squeezes again and tries to squeeze the carbon hard enough to start another nuclear reaction, but it doesn't happen. There's not enough mass to heat it up enough. So what happens is the star forms what's called a white dwarf, and the remaining gas sort of effervescence, floats away, and forms what's called a planetary nebula. And that's what we're looking at here. And they're all a little different. None of them look alike. They all are called planetary nebulas, but they don't resemble each other. They're all quite different. In this case, the leftover star, the white dwarf, is right in the middle, and this remaining gas is is a combination of, there is some leftover hydrogen, some leftover helium, and other gases, and so that's what we're looking at here. And it's called the dumbbell because there's a sort of a dumbbell shape. If you look here, there's a dumbbell, one arm with a dumbbell, and here's the other over here, and then it's got these 2 points sticking out. But anyway, that's why it's called a dumbbell nebula.
So long story short, this is what we have to look forward to in about 3.5 billion years when our sun starts running out of fuel.
Right. Yeah. It's gonna do something like this. It's going to become a white dwarf. White dwarfs are very interesting because they are very dense matter, way more dense than matter that exists on the Earth. I mean, I think 10,000 times more dense than normal matter. Not as dense as a neutron star, but dense, very dense nonetheless.
Yeah, so when our sun gives up the ghost and becomes a planetary nebula, basically the whole solar system gets reduced to a big puffball of gas. Interestingly enough, though, in recent years, astronomers have actually been discovering planets that are orbiting around white dwarfs, which is really weird because we used to think that all planets would probably be destroyed in the planetary nebula phase of a star's evolution, like we're looking at here. But it seems as if some planets can make it through that phase without being destroyed, or that they actually form out of the debris left over from the planets that were destroyed. But we really don't know yet. Mike, have you been reading about that stuff?
No, I haven't. That's interesting. I had not heard about that. Well, because the planets that are further away, what's going to happen to the sun even before it winks out? It's going to become a red giant too, and its orbit is going to get very large and might actually subsume. We're almost guaranteed to subsume the planet Venus. It might even subsume Earth. But the outer planets, Jupiter, Saturn, etc., probably it will not. And they might get a lot warmer, and maybe there will be life on some of the moons of those planets. But then it will once it goes through this this phase where it becomes a real red giant. It will, and that's the phase where it's burning helium. And once it goes through that phase, it will and winks out. It will shrink to almost nothing, and the gas that's left over will just effervesce. But the larger planets might still survive, the ones that are further up.
Yeah, and that's exactly the type of planets that have been found around white dwarfs, these huge gas giant planets, similar to Jupiter and Saturn.
Right. Yeah.
There's
a lot of excitement right now about looking for signs of life on some of these moons, because the tidal forces that exist around Saturn and Jupiter heat up these inner moons to the point that there's liquid water on these moons, not on the surface maybe, but underneath. And who knows, there could easily be some form of life in these cases. And so there's planetary missions that are being planned to look at like Europa and other moons of Jupiter and Saturn. Okay, so move on to something else. Should we try another planetary nebula, which is very close to here? So let's see what M57 looks like,
sounds great, Mike. And while you're moving the scope over there, I'll show folks some pictures of the Dumbbell Nebula that you recently took, as well as the moons of Jupiter, since we're talking about them.
Right.
I'll show you the moons that Mike was just talking about. So these are the 4 largest moons of Jupiter, known as the Galilean moons. Io on the left, Europa, Ganymede, and Callisto. And the moon that's most interesting in terms of potential life is Europa. We think that Europa is covered in a thick icy crust, but down below it, there's probably huge liquid water oceans, potentially more liquid water on Europa than there is on Earth. And if these oceans are anything like the oceans here on Earth, there could be deep sea hydrothermal vents and abundant life living down there at the base of these oceans on Europa, far from sunlight, just as life exists here on Earth. So yeah, a very tantalizing prospect for life in our solar system, and potentially complex life, not just the microbial life that we're might be finding on Mars or Venus someday. Let me show you that picture of the Dumbbell Nebula now. Mike, I think you recently took this image, right?
Yeah, I've not seen the one you're showing, although I could stop my own sharing and take a quick look at it.
Oh, this
Oh
is
yeah,
great.
that one is a very interesting picture. That's fairly recent. I took it last year, not this year. And what's interesting about this is that the normal image you see of the Dumbbell Nebula is this inner part of it, and kind of what we were just looking at. And but this, the outer part is only shown in narrowband images. So that that blue color there, in this case, is oxygen. And this is actually, I've maintained the true color palette. So the red in this case is hydrogen, and the blue-green is oxygen. And so that only shows up in a narrowband image. But to get these, make it a narrowband image and to see the detail, you have to expose for a long times, because what you're doing when you're looking at only the emission from a hydrogen or oxygen atoms is that you're eliminating most of the light that exists in the image, and you're being very selective. And that's part of why the Hubble telescope uses mainly the narrowband, because it's more scientific. You get more information about what's actually going on, and you're not just glomming all the light together like you see in a normal black and white or a color picture. You're only looking at the atomic, the light from these atomic species. This particular picture, I've merged an atomic picture with a true color picture, so we're seeing the two together.
And this was what, about 100 hours of exposure time, Mike?
Well, it's not going to be that much, because my longest picture is only about 70 hours. So I would guess this one is on the order of 20 some hours.
Okay, that's not that long.
Yeah.
Cool.
Because it is fairly bright. Even the fact that we can see this in a 20-second exposure, it means it's a fairly bright object. But these outer areas are not nearly as bright as that center area is, and so those, to get that outer area picture, it took. I think you can get a fairly decent picture in a matter of several hours of the inner part, but to get that outer part, it takes a lot longer. I do have M57 up, by the way.
All right, you can
and so
share your
we
screen
can
when you're ready.
Yep, I can share my screen again, and let's see. Okay, so there it is. So this is another planetary nebula, and you can see it's right next door, by the way, to this one. It's they're both very close to each other in the sky, almost dead overhead right now. And the white dwarf is visible right there, and you can see the halo around it. And this also is one where I have taken a 60-hour image of this in narrowband. I don't know that you have that available, Samuel, but again, there are clouds that extend quite a ways around this. If you look at it for extremely long times, like 60 hours, you can see these clouds. But this again is another planetary nebula. This is another one which you can see in a telescope, and I'm sure if you've been to some of Samuel's star parties, you've probably looked at this through an eyepiece.
Yeah, it looks very similar to what we can see right now in the image when you're looking through the eyepiece of a telescope.
Right. So
I'm just pulling up your narrowband image of this, Mike. I can show it to everybody if you
want.
want.
Okay. All right. Cool.
Yeah, it's really beautiful. You can describe a little bit about what we're seeing.
Yeah, yeah. So there it is. It's called the Ring Nebula because not so much because of this inner part, and you can see quite clearly the ring part of it. But if you look carefully, you'll see there's a lot of detail that you didn't see. You just saw in that previous image, you just saw even the ring has got detail in it. But then as you go out, there's two layers of outer, you can see these outer areas. And in this case, the red is hydrogen emission. And the outer area looks somewhat orangish because it's a combination of sulfur emission and hydrogen. Sulfur in this case is green, and you add green and red, you get sort of orange, and that's why that orange color. Look up, point to the other little galaxy that's in this image too. There's up in the upper left. Isn't that cute? So you're actually seeing a galaxy. I don't know how far away this one, but this galaxy, all of these objects we've looked at so far are nebulas in our own galaxy, in the Milky Way. And there are modest distances. They're long ways. This, I forgot how far this one is away. It's probably says here in the text, but my guess it's on the order of several thousand light years, 5,000 light years away. That galaxy in the distance could easily be tens, 20s, 50 million light years away. And so other galaxies, the closest large other galaxy to us is 2 million light years. It's the Andromeda. So we're talking about a different scale. We're talking about thousands of light years for these nebula in our own galaxy, and millions of light years, and in some cases trillions of light years, but in this case millions of light years probably to the distance, that other galaxy that's in the background.
Speaking of galaxies, should we go to Andromeda next?
See if we if hopefully it's not in a cloud right now, and we can go.
We'll find out soon enough.
Okay, I was going to go back to share my screen.
All right, you should be able to do that now.
Okay, and okay, so we're going to go back to the. While we're still in this area, let's just on the outside chance it looks better. Let's try NGC 6962 again. Just give it one more shot.
Sure.
In case it's cleared up a little
92
bit.
92 as opposed to 62.
I keep on, because I wrote it down wrong. 92, right. 9. Okay, there you go. Okay, it's very close by, so it won't take the telescope long to get there, and I can take a quick picture, and we'll see what it looks like. All right. Okay, there we go.
So this is that supernova remnant that we tried to look at before, but there seemed to be a little bit of haze around it last time.
Yeah, we saw it more clearly earlier, but we'll see what it looks like now. Only takes a... Yeah, I think it's better.
Wonderful.
Yeah, it's better.
Oh, yeah.
Just unzoom it a little bit. Yeah, much better. Now let's see if I can brighten it up some.
Yeah, there you go, right there.
Right there, yeah. Yeah, so that cloud that was there has left us. So all this wispy areas here are the emission from mostly oxygen gas and some hydrogen as well. So this in color is, as Samuel was showing, is nice blue, green, red image. Yeah, yeah, it's lacy. It's really beautiful. The Veil Nebula, I have taken pictures of all pieces of the Veil Nebula. This piece, the piece that's called the Witch's Broom, and the Pickering's Triangle, and it's really quite stunning. And I even have a picture of the whole thing I've done with my 6. I'm lucky enough to have more than one telescope in my observatory. I have a 6-inch telescope, which has a focal length of if I open it wide up with a focal reducer of 900 millimeter. This telescope is 3,500 millimeters, so it's a quarter of the well, it's a quarter of the focal, so I can get a much larger field of view, and I can get the whole Veil Nebula, not in single picture, but in several pictures. I can put together a mosaic of the entire Veil Nebula. But anyway, I enjoy doing that, having a picture of the detailed parts of the veil with the 20-inch, and then the larger perspective with the 6-inch telescope.
Actually, a picture he took of that photo I bought from him.
Yeah. Yeah.
What we're looking at right now is what he just took a picture of, that photo that I bought from him.
Yeah,
Okay.
I'll bring up the full image, Mike, so everyone can see what the
Okay.
entire Veil Nebula looks like. So we were just looking at this little area right up here in the upper right-hand corner, and Mike was talking about the witch's broom, which is down here in the bottom left, and then this is Pickering's triangle in the bottom right. So you can see just how utterly destroyed this star is, and how far the gas is just wafted out in different directions over the past 10 or 20,000 years since the star exploded. And I think red is hydrogen here, Mike. Blue is oxygen.
That's correct. Yeah. Yeah. So this is fairly close to the real color of this object, even though this is a narrowband image, false color, but it's close to the true color. Not that you could ever see it with your eye. Your eye this is all too dim, and it takes a fairly long exposure to bring out the color. But this is in fact what the colors really are.
You can see a little detail of this wispy gas in the witch's broom through a 20-inch.
We did. We looked at it earlier. The trouble is this bright. What you see when you take a picture with the narrowband filters, it knocks down the brightness of the stars that are in the image. And this, but when you look at it like we're doing now with a broadband, what we're doing now is looking at it with basically no filter in front of the camera. The camera is a black and white camera, and I get a color image by taking it through these various filters and assembling the picture, the color. But when you take a picture through the clear filter, which is what we've been doing, the stars, a bright star really becomes dominant. And one thing nice about taking the pictures in the narrowband is that you really dim down these bright stars, and you get to appreciate the detail in the nebula itself. And in fact, in my more recent processing of the pictures I'm doing now, I have a new technique that I can actually eliminate all the stars in the image, then work on the picture, the actual picture of the nebula itself, say, and then put the stars back. And so I can independently work on the nebula without having the stars being in the way, so to speak. And then I put the stars back because they're there and it's a part of the image. But I can make the stars, if I think the star this is a little bit where artistic comes in some of these pictures. If I think the stars disrupt the picture, I dim them down. And if I think they're okay, I brighten them up. In picture, so in these false color images, you have a little more latitude in doing all of this. In pictures of the galaxies, we'll go to a galaxy next. Those are true color, and they are what they are. And I don't play games like that because you can't. A galaxy, you only take in a true color form. But anyway, enough pontificating on this subject. We'll move on. Yeah.
So as Mike mentioned earlier, everything we've seen so far is inside of our galaxy, inside the Milky Way. But this next object we're going to look at is an entirely different galaxy. Our closest galactic neighbor, the Andromeda Galaxy, just over 2 million light years away.
Unfortunately, this isn't going to be that spectacular. We might see a few details, hopefully the clouds. I guess M51 is finally gone out of view here.
We actually should still be able to see M51. It should be above the horizon. We
Okay.
can check that out first if you want.
Well, that one will be on the right same side as the telescope is now. So maybe
Sure.
it's worth looking at that first.
Yeah, let's do
Okay.
it.
Okay. So let me share my screen and.
Sure.
M51 just happens to be, it has the nice feature that it shows out more detail, even though it's not as bright as the Andromeda. Andromeda doesn't have a lot of surface brightness, and you have to, but the M51, and also the other problem with the Andromeda with this telescope is huge. The Andromeda is something like maybe 3 or 4 moon diameters in size, and this telescope's field of view is basically 1 moon diameter, and so you don't get to see the whole galaxy. Whereas with M51, the galaxy fits inside this field of view very well. So anyway, well, let's go for it. M51, find. Okay, yeah, it's way down there, but we'll see what happens. Yeah, telescope's going to go there. I can tell you how high it is above the horizon when it gets there. It's going to be fairly low, I think. But
yeah, it is. It's fairly low, but we've been looking at it the last few nights on our stargazing programs.
Okay, well, good. So maybe it'll show up. Yeah, the program here, you can't see it probably in detail, but it tells me what the altitude of the telescope is. Now we're 35 degrees, 33, 30 degrees. Okay, well, it's 25, 23, 21, 18. Okay, 17 degrees above the horizon. So that's still not, yeah, that's okay. Hopefully, there's nothing obstructing it, but we'll find out very shortly.
We will.
Okay. All right.
As
So
we're exposing the image, I'll bring up one of your processed images.
Okay.
So folks can see what this thing looks like with a lot of exposure time.
Yeah, this one I've really done a fair amount of. This is almost 60 hours of imaging.
You can really see the sweep.
Oh, I know what the problem is. I've got to open up the. We're looking at. I have to.
I got to open up the dome a little more.
I've got to open the dome more because it's okay. And let's see, it's in the southern sky, right? No, northern.
No, northern sky.
Northern sky. So I've got to open it up. I got to open up the.
Yeah, so you'll notice there's more than one object in this image. There's the large galaxy down at the bottom here, and then there's this smaller little blob up above it. Obviously, the galaxy on the bottom is a gorgeous spiral galaxy. The one on the top is a little irregular dwarf galaxy, and it's literally going to merge with this larger galaxy. The gravitational field of this larger galaxy is much stronger than that of the smaller galaxy. So this small one will be completely subsumed into the large galaxy in the next couple 100 million years or so.
Well, we're actually getting an image. It's not as good as it was a month or two ago, but it is visible, and
Right. Yeah.
So there it is. Yeah. Yeah, this is the reason that one took something like 60 hours, that picture that Samuel was showing, is that this is actually a small galaxy. It's only about, let's see, about 8 arc minutes in size. So it's about a fourth of the field of view of my 20-inch telescope. So to get the detail that is in that picture, you just need to take a very long exposure to get the signal to noise extremely high, so you can actually drill into it and sharpen it and bring out the detail. And if you don't do that, all you're doing is sharpening noise, and that doesn't work. But here it is, and in a 20-second exposure, not a 60-hour exposure. And you can see, you know, the major features, the smaller galaxy and the larger one. The smaller one is rotating, and eventually it will merge, and there will be a single galaxy. This is, to provide a point of scale, I think this is on the order of 25 million light years away.
That's right. Yeah. So not bad for just a 20-second exposure of something 150 quadrillion miles away.
Yeah. And you know, and what you have to understand when you say 25 million light years, okay, so what does that really mean? That means that the light leaving this thing that we're now looking at left this 25 million years ago. So think about what was going on Earth 25 million years ago. Mankind didn't exist, you know, so I mean, the Earth was a very different place than it is right now, when the light that we're now looking at actually left that galaxy. And as far as we know, that it's possible that this galaxy has now merged. We wouldn't know that. You just don't know.
Mike, we just had a question from someone asking us to explain barred galaxies.
Oh, bar.
Yeah.
Yeah. Hubble, one of the other things that Hubble is well known for is characterizing. He came up with a scheme for characterizing galaxies. And the center part of a galaxy, in I think the Milky Way has a bit of a bar shape to it in the middle. This does not, but I don't know exactly what it is that causes a galaxy center to have a bar shape versus just a round shape. But and this galaxy, like the Andromeda and like the Milky Way, is called a spiral galaxy, and these arms are formed during the formation of the galaxy. Generally some spinning motion occurred, and the forces of gravity brought most of the mass in the galaxy is in these spiral arms, is not in between, and that's where the light is emitting, because the light is coming from stars that are in this galaxy, and also new stars that are being formed in these spiral arms. And the shape of the exact details of why the shape is what it is in some cases still a matter of research.
Now, I brought up a picture of some different types of galaxies and can show you a little bit about those. But as Mike said, we don't totally understand how all these shapes form. So the barred galaxies that we're talking about, and these ones in the upper left, still sweeping spiral arms, but the center of the galaxy has this, you know, fairly prominent bar shape. And then we've got spiral galaxies like the one we were just looking at. In fact, that is the galaxy we were just looking at, Messier Object 51, the Whirlpool galaxy. We've got irregulars that don't really have any well-defined shape at all. We've got peculiar, which do have some semblance of either a spiral shape or something else, but well, they're peculiar. And then we've got elliptical and lenticular galaxies. And the current theory is that after you have galactic interactions between multiple galaxies, such as these two galaxies that we just looked at, or of the Milky Way galaxy and the Andromeda galaxy, which will likely merge together in 3 to 4 billion years, you might end up with elliptical galaxies or lenticular galaxies after two spiral galaxies merge together and the spiral arms get distorted and destroyed from that interaction. But we're still learning a lot about this. And this is a process that takes place over hundreds of millions or even billions of years. So it's a difficult thing to study in one snapshot of time.
You know, the spiral galaxies are the more interesting ones to look at. They're also the ones they're active. Spiral galaxy, the fact that the arms are still there is also an indication that there's stars are being formed. The galaxy is active. Whereas when these elliptical galaxies are much older, they're merged remnants of several galaxies that merge together to form a single galaxy, and the activity in the galaxy is way down. Now, interestingly enough, I now have positioned the telescope on the Andromeda, and as Samuel was saying, the Andromeda and the Milky Way will merge in about about the same time as the sun is getting close to winking out. These two, the Milky Way and Andromeda, are going to merge. It'll be an exciting time for all, but
no one will be around to see it.
No one will be around to see it, at least on this planet. Okay, well, there's the Andromeda. So the Andromeda does, we can see it, and it's actually in clear sky at the moment, and we can see some of the structure in this image of the Andromeda. I'm going to dim down.
Yeah, go the other direction.
A little bit.
Yeah, just back where you had it, Mike. We were seeing some cool detail there for a second.
Yeah, let me. I'm going to get this guy this piece out of the way.
Great.
Bring this up. Okay, so
maybe reduce the zoom a little bit so we can see the whole thing.
Yeah. Well, we're not seeing the whole. We're only seeing the center part anyway, because this is we're seeing just. But I can.
Yeah, I think if we zoom out and then adjust the histogram, we'll see the extension of the disk a little bit.
Yeah. I could try to brighten it up as much as I can, but that's as bright as I can get it.
Yeah. On the edge there, we could start to see a little bit of detail. Yeah.
Oh yeah, you definitely are seeing detail
right
there.
In there.
If I
and so we can these dark areas just at the edge down here are actually dust lanes that are blocking the starlight from behind them. It's a little tricky to see, but oh yeah, that's better.
Yeah, I think the zoom in helps, because yeah, you're seeing some of these lanes here, down here in particular. See this lane? That's a dust lane here, right there. These are dust lanes. This image, this picture with this telescope is not all that interesting, because the galaxy is actually way bigger than this field of view. We're just seeing the center part of this galaxy. Of course, we're looking at the brightest part of it as well. But you are seeing more than you would see through an eyepiece, because in an eyepiece, this is spectacularly uninteresting. But because it just kind of looks like a dull cloud that you see some shape to it. But with the camera, in even this 20-second picture, you can see the detail, some detail here, detail here, detail here. And in my picture, if Samuel showed, this is what got me interested in doing astrophotography. I'd seen beautiful pictures of the Andromeda galaxy, and I said I would like to do this. And so my first really good picture that I put a lot of effort into was of the Andromeda. And maybe that's getting close to the end of the night for us. But I should mention that I was going off on a tangent here a little bit, but I should mention that the local group of galaxies, which is about 30 galaxies, most of them are small. Andromeda is the biggest one, Milky Way is the second, and M33 is the third. But then there's a bunch of really small ones. They're all gravitationally bound and over time are going to merge into a single large elliptical galaxy. And over time, meaning probably hundreds of 100 billion years. 4 billion is when we're going to merge with the Andromeda, but eventually it will all be a single galaxy. And all these other galaxies that we're seeing, like M51, we won't be able to see anymore, because the rest of the galaxies in the universe are moving away from us. And if this dark energy continues to exist, and it probably will for at least a long, for a long time, they're going to speed up, and at some point, these other galaxies, even M51, is going to be moving away from us at the speed of light, so we're not going to be able to see it anymore. And so 100 years ago, when people were looking at the universe, they thought the Milky Way was the universe. At least that was one school of thought. And then Hubble and others said, no, we think these other things that you're calling nebulas are actually other galaxies. And sure enough, they were right. But in 100 billion years, maybe trillion years from now, when people look out, if there are people looking at that time, they're going to see a single galaxy, and that's all they're going to be able to see. And what they will see, as far as they can tell, unless there's really good records of past history, they're going to call the galaxy that they're in the universe, because that's all they're going to be able to see. And that's what people 100 years thought was the actual case. They were wrong, of course, but in the far distant future, that's all there is going to be able to be seen.
And this conversation is pretty apropos with this picture being shown, because this was one of the very first galaxies that was in fact determined to be a separate galaxy by Edwin Hubble. Edwin Hubble looked at a specific type of variable star in this galaxy called Cepheid variables. And he used the relationship between the brightness of a Cepheid variable and how fast it pulsates, a relationship that was determined by probably the most famous woman astronomer of all time, Henrietta Swan-Leavitt, to determine that this galaxy was well beyond the edge of the Milky Way. And he did the same thing with several other galaxies and determined that most of them were moving away from us. And that was really the beginning of the understanding of just the vastness of space, as well as the expansion of the universe. But it all started with Andromeda here. So it's kind of cool that we're looking at that while talking about the future of the universe, as well as the fact that this was the image that got Mike interested in taking astrophotography or doing astrophotography. And I've got his image of Andromeda up here. So maybe we can end with this for tonight. We were looking at this area right in here. We were seeing a little bit of this dust lane.
Yeah, we were looking at the dead center of it, but yeah, we were seeing some of this stuff up here. A little bit there, a little bit. I think we were seeing this little thing here.
Yeah.
Yeah, and some of these patterns down here. Yeah, as Samuel was showing. Yeah, but as you can see, it's quite large. It's quite beautiful. Yeah, this image, if you look closely, you'll see little areas of red. And these little areas of red are places where stars are being formed. And I should also say, all the stars you're seeing in this picture are in our galaxy. But yeah, and these big blobs are actually neighboring galaxies that are gravitationally connected to the Andromeda, those two. And what look like stars in the lower left, my cursor won't show this, but right up here in the band area near the tail, those are actually huge star clusters in the Andromeda galaxy. But yeah, that's what I was pointing at. Those things, those are actually in the Andromeda galaxy, but they're not individual stars. They're huge clusters are probably hundreds of thousands, if not more, stars each. But Hubble, with the telescope, the 100-inch telescope, was actually able to image individual stars in this galaxy, and he found this Cepheid variable star that allowed him to measure the distance. Because for a good part of the 20th century, that was the name of the game. How do you measure distance to stellar objects that are way out there, objects that are very far away? Close objects you can do by parallax. When the Earth is on one side of the sun and on the other side of the sun, you measure the difference in position. But that only works for objects that are relatively close. Now we're getting better at that, but to really get an accurate measure of distance for objects where the parallax difference isn't enough, you have to have what are called standard candles. And the Cepheid is a form of a standard candle. The form of the standard candle that's probably used now mostly is a type of a supernova, which are called class 1A supernovas, which happen to be all about the same brightness. And so if you see one of these things and the brightness is more or less the same, then you can measure its distance.
Well, everybody, we're about at the end of virtual stargazing for this evening. Thanks so much for joining us. And yeah, we'll continue to do this occasionally on clear nights out here in Jackson Hole. We'll look at different objects as the fall and winter progress. There are some really cool objects that we can see in the wintertime that we haven't yet imaged this year. So yeah, check back in a little bit with us, and we'll show you those objects next time around.
Yeah, it was interesting when we started these virtual stargazing. We were actually looking at Orion. We still were seeing Orion in the spring, and that is coming back.
That's right. Yeah, another month or so we should be able to see it.
Yeah, if you stay up late at night and you look at the sky at 2 and 3 in the morning, you'll see Orion.
Yeah.
It's coming back.
Thanks again, folks, and have a great night.